This is Module 15, Section 8.2. In this section, we're going to continue our discussion on functions and start with an introduction to functions. So to start, pretend you have two sets that are related or correspond to each other. So we're just going to say we have a first set and a second set, and we are going to say that those sets are related in such a manner where if you had, let's say, something that you just represented with just a general A, when you put A into this relation or correspondence, you would always get out something, say, B. Or maybe you put in C in that first set, and when you put C in that relationship or that correspondence, you got out some other value D. Okay, now, since we're talking about math here, usually these relationships or correspondences do deal with numbers in some way. In theory, it could relate to anything. You know, maybe you put in fertilizer and you get out longer grass, or maybe you water your flowers and your flowers grow. There doesn't have to be a mathematical relationship, but this, of course, is a math class, so we're going to consider numerical relationships primarily. Now this first set, we're going to give this a new name. We're going to call it our domain. And in this class, since we're talking about the relationship between two number sets, we're going to let the domain represent our x values in our relationship. Okay? So our first set is going to be our domain, and our domain is going to be our x values when we're talking about equation work. Our second set then is also going to have its own title. We're going to call the second set our range of values. Okay? And our range is going to be represented by our y values. So if we're talking about a relationship where we maybe have ordered pairs, you can represent this type of correspondence with ordered pairs. You know that in general, ordered pairs are usually x comma y, and so for this type of discussion, x values are our domain and y values are our range. So if you ever see an ordered pair, it will always be domain comma range for our purposes. Now the way we set up relationships or correspondences often, not always, but often is through the use of an equation. So let's look at this equation and talk about how the first set or the domain relates to the second set or the range. And we're going to stick with this tabular form because it's the easiest way to introduce functions, I think. So for our first set, remember we said our first set was going to be our x values. Let's say you decided to let x be 0. Now you can see that if you put 0 in for the x value in the equation to my right, you're going to get 3 times 0 plus 8, or 0 plus 8. And when you put in 0 for your x, your y value ends up being 8. So we choose our value of 0, and we get out 8. Let's say we decided to pick a domain value of 2. If we put 2 into that equation, we get out 14. If we choose, let's say, to pick -1, if you put -1 in that equation, I believe you get out 5. So there's an obvious relationship or a correspondence between the first set and the second set. Notice that your y value depends on what you choose for x. Therefore, when you set up a problem as in the previous slide where you have your equation solved for y, x is the independent variable because you usually choose the x value first because the equation's easier to solve that way. X is your independent variable, and then y is dependent on what you decided to let x be. So now let's define some terms for the type of relationship we might have between sets. There are two basic relationships that we are interested in. The first is defined like this. If each member of the domain, and remember domain is simply your x values, if each member of the domain corresponds to at least one member of the range, which is y, then the correspondence is a relation. Now that's a fancy technical definition. What that really means is x can be assigned more than one y. So let's look at this relationship here. Y squared is equal to x. There's definitely a relationship between x values and y values there. And you would agree with me that if you let x be 25, that's your domain. If you let x be 25, there are really two y or two range values that you could use. If x was 25, then you'd have y squared is equal to 25. If you solve for y, y could either be a positive 5, because 5 times 5 is 25, or y could be a negative 5, because negative 5 times negative 5 also is a positive 25. So if we put in or choose to let x be 25, then our range value could be a positive 5, or it could be a negative 5 for the same domain value. According to this definition, as long as you have at least one y value for each x value, in this case we have 2, then we're said to have a relation. The second type of relationship is defined like this. If each member of the domain corresponds to only one member of the range, then the correspondence is said to be a function. So a function is a special type of relation. It's like a subset. And it has stricter rules. The rule is, for a function, x can be assigned only one y. And so the above example that we just talked about here, where 25 or x is assigned two y values, although that was a relation, that is not a function. Okay? But the equation that we talked about on the previous slide is a function. Notice that for each x value we put in, we got out only one y value. You never got out two y values or three y values for any one x. So if you put in one x and get out one y, then that's said to be a function. So let's look at some examples and talk through that a little bit. We're still just going to use a general tabular or table form so that we can talk about it in a simple fashion, and then we'll expand that to something that maybe isn't just a few ordered pairs to look at. So the question is, are the following examples relations, and are they functions? And the first example says this. If you put in a domain value of a, and let's say you get out 1, and you put in a domain value of b and get out a range value of 2, and put in a domain value of c and get out 3, the question is that a relation? Well, all a relation says is, if you put in an x value or put in a domain value, do you get out at least one y value? And the answer here is yes. You agree that for each x we've got at least one y value. And so the answer is yes, this is a relation. Now, is it a function? A function is stricter in its definition. It says that for each domain or for each x value you put in, do you get out only one y per x? And in tabular form, the easy way to think about that is there only one arrow coming out of each of those x values? If the answer is yes, and the answer is yes in this case, then the answer to the question is yes, this is also a function, because we're getting one y value out for each and every x. Notice that that's the same relation or function could be listed out in ordered pair form if you wanted to. This would be a comma 1 and b comma 2 and c comma 3 in ordered pair and then roster notation. Okay, second example. Let's say in this example you put in a and you got out, let's say, 16, and you put in b and you also got out 16, and let's say you put in C and got out 4, and you put in D, whatever D represents, and you also got out 4. Same questions. Is this a relation? Well, the answer is yes. Notice that for all of the domain values, we're getting at least one y value out. So the answer is yes, this is a relation. And in fact, almost everything is a relation. Okay? If there's any kind of ordered pair relationship at all, it's a relation. Is it a function, though? For each and every x value, are you only getting one y value out? And the answer again is yes. Notice it doesn't say you can't reuse y values. It just says when you put in an x, are you getting just one y value out for each x? And the answer is yes. You put in A and you get out only 16. You put in B, you get out only 16. You put in C, you get out only 4. You put in D, you get out only 4. There's just one arrow coming out of each of those x values. Okay? So the answer to this is yes. This also is a function in addition to being a relation. And an example of that in terms of an equation where you might see something like that might be an example like this. Let's say you had x squared equals y. Notice here, you could put in an x value of 4, okay, and 4 squared equals 16. So for example, A here might be 4. Or you could put in negative 4 for x. So in this case, let's say B was negative 4. And if you put negative 4 in and square it, you also get out 16. Same value as shown by these arrows. Okay? Or here, C could be 2 and negative 2. You get out the same y value, but as long as you're just getting one answer out for each x, then you still have a function. And that, of course, could be listed in ordered pair form as well, if you wanted to. All right, let's look at a third example. Let's say you put in some value represented with an A, and you get out a positive 5. Then you also could get out, using that same x value, you might get out a negative 5 as well. Or maybe you put in B, and you could get out two answers, 6 or negative 6. Is that a relation? Well, yes, nearly everything's a relation. That is a relation. There is some correspondence between your x and your y values there. And for each x you put in, you get in at least one y. Is that a function, though? And the answer to that question is no. That's not a function because, in this particular example, for each x value you're putting in, you're getting out two y values. And that's not allowed to be a function. It's fine if it's a relation. It's not if it's a function. Visually, you can see there are two arrows coming out of the same domain value. And a practical example of that might be this equation, y squared equals x. Notice here, let's say that you chose to let x, or our a value here, be positive 25. If you put 25 in for x and you solve for y, there's two possible answers that could be. If you take the square root of both sides and solve it, you see that y is equal to a positive or a negative 5. Two possible answers. So if we split that out, positive 5 or negative 5, which is what we have up here, for each x value you get two answers out. That, by definition, is not a function. Okay, so let's look at some forms that are not tabular form and talk about whether they're relations or functions. Are the following relations, are they functions? State the domain and range of each. Now, if this is new to you, you certainly could write these very simple correspondences in tabular form if you want to, and I think I'm going to do that just for discussion's sake. To determine the domain, remember domain is simply the x values in any type of representation. So in this case, we've got x values of 6 and 5, which is used twice, and 7. Okay. our range values for this first example are 6 and -2, and then 6 again. So the range value of 6 is used 3 times, and the range value of -2 is used once. Now, represent the correspondence with arrows if you're going to use tabular form. For this first ordered pair, if you put in 6, you get out 6. Second ordered pair, you put in 5, you also get out 6. Third ordered pair, you put in 5 and you get out -2. And fourth ordered pair, you put in 7 and you also get out 6. Is this a relation? Is there some sort of correspondence between the x and the y values? And the answer is yes, this is a relation. Nearly everything's a relation. Is this a function, though? And the answer is no, it is not a function. And the example that keeps it from being a function in this particular demonstration is that 5. Notice that when you put in 5, you get out 2 y values for that single x value. That is not allowed in order to be a function. All right, the second example over here, okay, determine your domain. Domain is your x values, so you've got 1, 2, 3, and 4. The corresponding range values, in this case, notice the range values are all the number 1. And the relationship between those, you put in 1, you get out 1. You put in 2, you get out 1. You put in 3, you get out 1. You put in 4, you get out 1. Is that a relation? Yes, it is a relation. Is that a function? And the answer there also is yes. Function doesn't say that you can't reuse your y's. It just says for each x, there should be only one y. It doesn't say anything about whether it's the same y. As long as there's just one arrow coming out of each of those domain values, you're fine in terms of function. And so, yes, it also is a function because of those single arrows coming out of each x value. All right, so we can reuse y values all we want to be a function. We just can't reuse x values. To be a relation, we can reuse x values and y values, and it doesn't matter. Okay, so let's look at this graphical example. Again, if you wanted to, you could write that out as a table if that makes it easier for you. You've got domain values and range values. Okay, we've got ordered pairs here. I'm going to start with the ordered pair farthest to the left. This ordered pair right here is -2, +2. So that's -2x gives you a +2y. Okay, the second ordered pair, although that dot is a little bit off the crosshair, I'm just going to assume it's on the crosshair. We've got -1, +1, so we put in a -1 x value, and we get a +1 y value out. And then down here, we've got +4, -4, so you put in 4, you get out -4. Is that a relation? Well, yes, it's a relation. Is that a function? Yes, it's also a function, because for each x value, you get only one y value out. All right, so let's do the same thing with this example here. We'll look at our domain and our range values. Starting down here, and again, I'm going to assume that that's on a crosshair, we've got -4, -5. So when we put in -4, we get out a y value of -5. This value right here, we'll put it up there on that crosshair. We've got +4 and +3. So we put in 4, we get out 3. This value right here, again, we'll put it up on that crosshair. We've got +4 to the right and +6. So same x value, +4, also gives us a +6. And then our final value over here We've got 6 to the right and 8 up. So we put in 6, we get out 8. The questions are the same. Is that a relation? The answer is yes. It is a relation. Is that a function? The answer is no. This is not a function. And the thing that keeps it from being a function is that 4. Notice that we're putting in an x value and getting 2 different y values out of the same x value. So no, this is not a function. It is a relation. So what do you do if you have a graph rather than ordered pairs? Can you graph relations and functions? Yes, you have to have ordered pairs, and you do have ordered pairs, and therefore you can graph them. And that's true with an equation. If you have an equation, you can get ordered pairs and sketch a graph. Can you tell if a graph is a relation or a function just by looking at it? And it turns out that yes, it's actually quite easy. There's a test called the vertical line test for graphs to determine whether they're functions or not. And here's how it works. The vertical line test, or VLT, says if no vertical line can be drawn so that it intersects a graph more than once, the graph is the graph of a function. If a vertical line crosses the graph more than once, it is not a function, but is still a relation. Now, why would that be? Well, if you have 2 ordered pairs on the same vertical line, then you have 2 y values for the same x value. And if you look back at the previous example that we did on the previous slide, we had 2 ordered pairs that were on the same vertical line. And so for a given x value, we got 2 y values, and we said that's not a function. So here's how you apply the vertical line test. Here we don't have any equations. We don't really have any ordered pairs listed out, although we could look at the graphs and get some ordered pairs. The question is, are the following relations, and are they functions? And just to answer the first question for all three of them are relations. If there's any kind of graph, any kind of ordered pair relationship, they are going to be relations. So we'll just answer that for all 3. Nearly everything is a relation. Now, to determine if they're functions, though, here's what we're going to do. We are going to draw vertical lines along that graph and ask ourselves, do those lines cross the graph more than once at any one point? And you agree with me that the answer is no. It doesn't matter where I drew those vertical lines, the maximum number of times they crossed that blue line was 1 time only. And if that's true for anywhere you draw that vertical line, then the answer is yes. Because they only cross a maximum of once, you do have a function. Okay, now this downward facing parabola is the same way. You can draw a vertical line anywhere on that particular graph, and notice that each vertical line only crosses the graph once. Okay? So this also is the graph of a function. Now a circle is another case. Notice that I can draw a vertical line here and it crosses not once but twice. Now again, what that means is where x is equal to 2, I have 2 y values. So for one x value, I'm getting out 2 separate y values. That's not a function. Okay? Now sometimes students will say, well, yeah, but I can draw a vertical line where it only touches the line once. For example, if you're right on the edge of the circle, you could touch that circle only once. That's true, but it's not can you draw a vertical line that touches only once. The question is, do all vertical lines drawn anywhere only cross once? And the answer obviously is no. There's a lot of lines you can draw where the lines will cross not once but twice on that circle. So, although this is a relation, this is not a function because we can draw a vertical line that crosses the graph more than once. All right, so now let's talk about function notation. And we're going to talk about it in terms of how function notation was originally thought of, starting with an equation written in standard form, which was probably the very first form you ever learned when talking about graphs. 2x plus y equals 6. Now, if we take that equation and if we solve that equation or isolate our y value, which means we're going to get it in slope-intercept form, we would move our 2x to the other side, and we'd simply have y equals negative 2x plus 6. Now, you would agree that if you were given that equation, and I asked you to get some ordered pairs maybe on the line that was drawn by that equation, you probably would pick x values and solve for y because that would make your life easier. It's easy to pick x values and solve for y simply because you don't have to do any rearranging. You can just plug numbers in for x and put it in your calculator. So you would agree with me that the value that you're going to get for y is dependent on what you choose for x. And that's why when we talk about domain and range, your domain values, which are, in this class, always your x values, your domain values are also referred to as your independent variables. Because you're picking anything you want for x, and then you're solving for y or your range values. So range values are also referred to as your dependent variable. So the value of y is dependent on what you choose for x. Now that's true, but that's pretty wordy. And this is not an English class, this is a math class. So let's shorten that up using a different phrase. Y is dependent on what you choose for x could also be phrased like this. Y is a function of what you choose for x, or even shorter, y is a function of x. Same thing, less words. But again, since this is a math class, that's still way too many words for any self-respecting mathematician. So now we're going to symbolize that using mathematical symbols to shorten up the amount of writing we have to do. So looking left to right, we've got y is, you know from beginning algebra or even pre-algebra, always represents the equal sign in math. Okay? A function of, there is a mathematical symbol for that. It's a script f. That is not a variable. You will never solve for f like you solve for x. Okay? That script f just stands for the phrase is a function of. And then whatever the equation is a function of, you will put that variable in parentheses. In this case, y is a function of x. And take that equation at face value. What that says is y and f of x are equivalent. Therefore, if you have an equation that is solved for y equals negative 2x plus 6, you can replace that y with f of x and get an equivalent equation simply written in different notation. This is called function notation. But it's the exact same equation, means the exact same thing. However, you can only replace the y with f of x if y is isolated, because it's at that point that y is a function of x when y is isolated and dependent on what you choose for x. So in other words, don't do this. The original form of that equation was 2x plus y equals 6. You cannot, in this form, take that y and replace it with f of x. That's considered poor form and is not allowed. You first must solve it for y, and then you can replace the y with that function notation. Okay, so let's talk about using new function notation and how it compares to what you've been asked to do prior to this. Okay? In old notation, if they were to ask you this question, given y equals negative 2x plus 6, find y when x equals 2. Okay? That's a very simple problem. Okay? All they're asking you to do is take the equation, take the value that they ask you to substitute in for x and do the math. So you get negative 2 times 2 plus 6 equals negative 4 plus 6, which of course is positive 2. So we've got y equals a positive 2. With new notation, we can ask the same thing with a lot less verbiage. Okay? What new notation or function notation will say to ask the very same question is, given f of x equals negative 2x plus 6, same equation, different notation, find f of 2. Now do a direct comparison here. The problem is asking you to find f of 2. If you write that directly beneath the equation, notice that the x and the 2 correspond to one another, which gives you a hint that what you're actually letting 2 represent is the x in the equation. So what you're going to do is take that 2 and put 2 in for all of the x's in the equation. In this case, there's just that one x that's attached to the negative 2. And do the math as before. Negative 2 times 2 is negative 4 plus 6. And negative 4 plus 6, again, is a positive 2. Same answer, less writing to ask the question. Note that you might be asked to give an ordered pair, perhaps. Maybe you're going to use that information to do some graphing later. So notice the value that's attached to the x is your x value. Okay? And then your y value is the answer that you get out after you plug that value in. So in this case, our ordered pair is 2, 2. And of course, it's the same thing here, just written a little bit differently. All right, so let's practice using function notation. Given f of x equals 3x squared minus 4, and g of x, the reason they use g there is if they used f of x, you would get confused as to which equation they were talking about. So normally, when using function notation, if there's more than one equation, they will use lowercase script letters in alphabetical order. So f of x, g of x, h of x, etc. So f of x equals 3x squared minus 4, and g of x equals 2x plus 1. Find each function value. So part A asks you to find f of 3. What that means is you're going to put 3 in for the x in the equation and solve the equation to see what you get. So we've got 3 times 3 squared minus 4. Now it's just an orders of operation problem. So do the exponent first. 3 times 9 minus 4, which is 27 minus 4, which is 23. So f of 3 equals 23. If you were asked to put that in an ordered pair, remember x comma y, this is always your x value. The answer you get out is your y value. So 3 comma 23. G of 1/2, what that's going to ask you to do is put 1/2 in for your x and solve. So coming down here where I have more room, I've got 2 times 1/2 plus 1 equals, notice those 2's cancel out, 1 plus 1, and 1 plus 1, of course, is 2. So g of 1/2 is equal to 2. the corresponding ordered pair, x comma y, would be 1/2, 2. F of -2, okay, we're going to put -2 in for the x in our f function. So we get 3 times -2 squared minus 4. Follow orders of operation. So we've got 3 times -2 times -2 is a positive 4, minus 4, which is 12 minus 4, which is 8. So ordered pair, when we put in -2 for x, we get out a positive 8. All right, final example, g of 125, we're going to put 125 in for the x value in our g function. So we get 2 times 125 plus 1, which is 2 times 125 is 250, plus 1, 251. Or the ordered pair would be 125 to produce 251 for our y value. Now, a slightly different twist. You may be given a graph of a function and be asked questions in function notation. So here, notice we do have two functions. One is f of x, the other is g of x. You are not given an equation, nor do you need one, as long as you have the graph. Let's do this first question. Find f of 3. Now remember, you're going to assume that the independent variable is always in those parentheses. So f of x means we are letting x be equal to 3, and they want us to find y. So go to the appropriate graph, find where x is equal to 3. So in this case, 1, 2, x is equal to 3 here. Find where that is on your line, and then follow it over to the appropriate y value. When x is equal to 3 on this line, y is equal to 4. So y is equal to 4, ordered pair 3, 4. Y is equal to 4. Find g of -5. Again, we're going to look at that second function, g of x. We're going to find where x is equal to -5, and we're going to find y. So if we come over here, x is equal to -5, 1, 2, 3, 4, 5. Looks like the corresponding y value is right on that 0, because that is the x-intercept. So where x is -5, y is 0. Okay, ordered pair, -5, 0. Now be careful on this next one. Find all values of x such that f of x is equal to -1. In this case, they're giving you the y value. Okay, they're telling you that y is equal to -1, and they want you to find the corresponding x values. Okay, so in this case, we're going to look along the y-axis on the f of x. Okay, find where y is equal to -1. That would be right here. Follow it over. Find the corresponding x value. The corresponding x value is -2. So in this case, the ordered pair would be -2, -1. And this brings us to the end of Module 15, Section 8.2 material. You should now complete the homework for Module 15, Section 8.2, found in my math lab. And when you have successfully completed the above homework, proceed to the video for Module 15, Section 8.3.